All right, so I want this idea of a list. So, real quick, I want this idea of a list where you can add and subtract lists kind of deal. So, or it's actually a tree. It's like a tree. So you have imagine you have, like this, for example, you have A, B, C, and then you subtract this with like, or you subtract this from it. Actually, let's just say this. And then the result of which would be something like this. Or it would be like, yeah. So I want this, and the reason I want this is because when we're describing some configuration, so we say, okay, we started with, so we have our setting, we have like, we pull from the network, we pull from Cloudflare, right? So here's Cloudflare, whatever, I don't know what this is. We have Cloudflare. And we pull the configuration. So we have a local configuration, which is the actual state. This describes the actual state, right? So this is a state. And then we want to describe our configuration file as recreating the state as much as possible to our fullest accuracy. So we have our Python script. We have our script, our program. Jesus Christ. We have our program which essentially recreates a target state. So like this is like ST. This is just S1. So the goal is how do we get from S to S1, right? And how do we get from S to S1? Well, if we have these semantics, then it's like a simple addition problem or subtraction problem. So we say, okay, S1, we say like, okay, the difference between, what is the difference between the current state and the target state? Well, that's easy. It's ds, which is literally just S1 minus S, right? So, and what does this mean? Well, ds describes like the difference in how to get there. So if we have, for example, let's say like we turn something from off to on. So let's have our S we have our S. Motherfucker, man, this is so annoying. We have our S configuration, and then we have our S1. So here's our S. And here's our S1. So our S is a tree in which there is some option that went from off to on. And then let's say like we have a list full of records and we delete. We have a tree full of records and then like we delete one of these records. So we have like record 0, record 1, record 2. And what we end up doing is we just delete. We delete a record. So if we delete a record, what does that mean? Should we preserve the index? Should we delete the index? I think we should just preserve indices because that makes things easier. Like we preserve indices because yeah, like that way all we're doing at the end of the day is deleting. We're not even deleting. We're not deleting anything. That's the whole point because we're not trying to change the structure at all. We're just trying to, we're literally just saying, okay, I want to delete R1. The way we can do that is literally by saying, here's our new state. R0, R1, just kidding, you're not there. Then we have R2. So this is how you delete. You just don't write it. You just don't make it. You never make it. And to be honest, I actually don't know if we can do that. Because when we're creating a list, these arguments are like, they're positional. You can't just, I don't think we can just put, because we can't really know what we're missing, I think, is the problem. So I think what's going to end up happening is we have R0, and then we have R1, and then, I'm sorry, not R1, we have R2, and then, like, I'm not really sure what has to happen here. There's going to be a discrepancy between these two, maybe, because this is not R1, this is R2, and then this doesn't exist, right? This just doesn't exist. So I'm not really sure what this is actually supposed to look like, but I think I know what should happen. So we should obviously go from off to on. We're going to keep this, and then we're going to remove this. We're going to remove this. Right? And then this is just going to get, I don't know. So this goes to on. Okay, we have these two structures, and then let's describe DS. So DS, can we make this canvas bigger? Background color. It should be white. Didn't even do anything. Alright, well, anyways. So we have these two states, and then we say, okay, well, S, what is S what? DS describes a new list or a new tree where, like, I mean, this is I think this is pretty simple because at the end of the day we're attributizing this. So we have like 0, 1, 1.0, 1.1, 1.2. You know, it's kind of, I mean, that's pretty much it, is the way I see it. And when we take the difference between these, we're just doing it component wise. We don't really have to think about it that much, I don't think. Like, sure, there's probably a different way we could describe subtraction and addition, but I think these are, for our use case, these are useful semantics, is that we just say we're subtracting each of these attributes directly. And yeah, so ds describes s1 minus s, which also describes this list or tree structure where we have on, okay, so look, we have one on, we have on minus off, which means that we have one on and we have -1 off, is what this means, right? This means we have one on and we have -1 off, and we don't care about we only care about how many, we only care about having I think we only care about having one on, one of anything, right? So in other words, this is just this, right? This is one on minus one off. And we don't care about having, we only care about any one or more amount of things, I think. And the reason for that is because, well, I don't care about having negative apples. It's not tangible to me. Only having any one or greater amount of apples is gonna provide me something. Otherwise, it's like negative matter, and that's not particularly useful. So now, okay, what's the next step? We have R0 and R0. Like, this is just going to be R0 minus R0. R0 minus R0. This is going to be R2 minus R1. Right? Oh my god. It's R1. And then this is going to be nothing, right? Nothing minus R2. As in this is just going to be nothing minus R2. And yeah, like that's it. So now we have this new tree which describes ds. So we have ds, right? we have ds, and then we could also have negative ds. And here's the cool thing about negative ds is because, okay, I think this is where the antimatter analogy comes into play, is that antimatter is there because we've subtracted it from reality. So, if we have some configuration like this, and we, in the case of like having text record or like DNS records, because that's what our config actually has. There are cases where we need to delete something before we can add it in, because there is like a constraint. What is it? There's a constraint which doesn't allow you to have like existing. You can't create something that already exists there. So the first step is to remove said thing, right? So if we have one on and we have a negative, like describing our difference, if we have one on, actually not even describing the difference, if we just look at it this way, our initial state is we have an off here. Our new state is we have an on. What this kind of really means is we need to delete off and then we need to add on. So like we're gonna delete you first and then we're gonna add you. Not in this order where we first add and then subtract, because there are constraints which don't allow this to occur. So basically what this means is we want to do an action on the negative ds before we do it with the positive ds. So the idea here is we say, okay, let's get the negative ds. Let's get the negative ds. And then we'll get the we'll just get ds. Right? We'll get the positive ds. We have the negative ds and then we have the positive ds. Right? And then we say, okay, you want to first what do we want to do? We want to delete the attributes, whatever delete means, and then we want to, okay, we just say this, like we want to, yeah, delete. This might be like a HTTP, this might be like a push, what is this? Like a delete request, HTTP delete. And then we might have like an add, or we just say create. So now we have good semantics of, like, these are good semantics, right? Because we only have to do it like this. We don't have to really think about it that much. If we can incorporate these semantics, which is a whole other hairy implementation that we have to figure out. And here's kind of another way, just like, not really thinking about it, because I'm not really good at algorithms. Which is why if I were to do this, and this is probably how I am going to do it, is we say, okay, how do you attributize a tree? So you say, okay, well, this is 0 and this is 1, and then this is, this is 0.0, and then this is 0.1. Because the idea is you're just going from left to right. Yeah. You're just going like this. Like, no, that's it. Like, that's it. You're just going like, I could not see the mouse. There's no fucking mouse. Okay. You just go like here. Is this shit gonna fucking work? Like, it's really easy. You just go 1, 2, 3. 1, 2, 3. So if we break down what this looks like, it doesn't matter. These could be like random things like Z, L, 5, for example. Let's break this down like if we were to attributize these components. And this will make it a lot easier. So if we say, okay, we have, and we pretty much only care about the leaves, I'm pretty sure, the leaf nodes. So we say, okay, here is like 0.0 is Z, 0.1 is L, and then, you know what? It doesn't matter. Let me just say 1 is 5. And so now we have like a like just a linear correspondence, and we don't have to think about the tree structure. So basically, like, what does this mean for us? Well, when we subtract something, like if we subtract it with another tree, for example, like let's describe what this means. You know, this is, we're just going to say this, for example. And we're going to say, like, I don't know, 2. And then we're going to say, well, if we subtract this with, you know, this, then this is like really actually this is like a really easy thing to break down now because it's pretty much side by side. And if it's not, and should it not be side by side because we have some extra thing, I don't know, like, should we have an extra thing in here? It doesn't actually have to be side by side because we have these corresponding things. So it's like, okay, we know that this corresponds with this no matter what. No matter if this is down here or here or wherever it is, which actually shouldn't be the case, but if there was an extra, like imagine if there was an extra thing in here, for example, like, then this would correspond with here, but not actually because these like indices are pretty much absolutely true. Like this is an absolute position. So I'm not really sure if what I'm describing makes sense, but like there's no ambiguity to be made. Like this certainly corresponds with this. And yeah, like I mean that's pretty much it, right? And this is not trying to find the minimum difference. This is just trying to find the difference as like if everything is like a positional index. Like we're not trying to say like, oh, what is the minimum effort difference that you can represent between these? Like that's not the goal here. The goal is to represent like index based difference. So okay, well what is the result of this? Well, we get a new tree. We get it, and like when I write it in this form, it's really the same as this. And when I write it in this form, it's really the same as this. So given that, we can understand that, like, I think we can understand what we're trying to accomplish here. So we have 0, 0, right? And then, well, what's 2? Sorry, not 2, z minus 2z. Well, this is just going to be negative z. and then this is going to be L minus shit. This is supposed to be 2. So we have L minus 2, which is just L minus 2. And then we have 1, and then we have 5 minus 5, which is just 0. So this is the result, right? And what does this look like? It just looks like this. And it just looks like this. I'm sorry. Also, what the fuck? I wrote 4 here. What am I doing? Which means that this is not 5, this is 4. And this, which means that 5 minus 4 is 1. So the result of our new tree is supposed to be like negative z 2 L minus 2 and just 1. And which means if we like that, which means in order to get from here, to get from here to here, we need to add this and this and this, and that will result in this. So, like, no, I mean it's really that simple. Like the whole idea is that we're just trying to create an algebra so that we can, like, we just want to describe it, this. We just want to describe, okay, a plus, this is all we're trying to describe, a plus b equals c, and then what is, and then we want to describe like subtraction, you know, and we want to describe, actually here it is, we're just trying to describe a plus b equals something, and then a minus, and then like b minus a equals something. Right, and then like these are just the semantics we're trying to create, and so yeah, like this is it. We just need to incorporate this, and the idea is we can delete. We can just delete negative ds, and we can create ds. So that's what we're trying to describe here. I use ChatGPT to make all this shit. But honestly, it's really awful dealing with ChatGPT. It's really awful. So what was the reason that I was doing this? So okay, so here's the shortcoming of the current way that we're doing. Here's the shortcoming of the current way we describe taking the difference between two lists. So the current way we're doing it isn't really, it's not really the same thing. Like, okay, we're describing the difference, but we're not describing, right now we're describing the difference, but we're not describing subtraction. Even though subtraction and the difference should be the same thing, right? But the reality is, the way that we have it implemented is not really the difference. It's more like, it's like anti-inclusiveness. So if I say, you know what it is? The way I'm doing it now is like a and not B, maybe. Something like that. I'm not sure. It's like A not B or something. Or B not A. Because let me show you. So we here's what describes diff. So let's describe diff for two trees. Right. Where basically this is like right minus left, but it's not really subtract. It's not subtract. If we just say A, B, C, then and then we have like A, C, C. Well, what it does now is returns you a tree where this becomes none. This becomes I'm pretty sure this just becomes B. And then this becomes none. And yeah, right, because this describes how we got from what was the difference required to get from A to B, I think is what this describes. Let's just test it. Let's test it. Let's see what it gives us. All I know is that these semantics are not right. This is not right. So let's describe it. So we have S0 where 0 is, what did we say? 0 is another tree. So 0 is a tree. 0, 0 is, what is this? It's A. Then 1 is B. And then S0, 1 is C. Okay, and then now let's describe S1. Well, we have ACC. Okay, now let's see what the result of diffing these is. Right, and we do, it's kind of backwards right now, but we do ABC. Yeah, I don't know, let's try it. None B. Yeah, see? Yeah, so it gives us none. And okay, real quick, to say that this is none is to say that it doesn't exist. So this is none B. Like that's exactly what we got. But it's not just none B, it's none B, right? It's none B. And because this exists within a tree, like this is a tree, and then this is also a tree. So it exists within. So it's actually not a tree, it's like a level of the tree. But I think you understand the point. So why is this bad? Why is this bad? Because because we kind of lose context of everything about this tree. It's not that we lose context, we make the problem a little bit harder because um, we make the problem difficult because what I really want is that we maintain context to everything before it, and we don't because none destroys it. It just gets rid of it, and I don't want to get rid of these things. I want to keep track of them so that I understand the scope of in which I'm working with. So right, because it gives me more insight. Like if even if like let me show you what I mean. So like even if I'm in this tree and I'm like iterating, I'm just recursing through this tree, traversing. Like I want to know I want to know all the terms because now that I kind of realize it, we can like start with negative terms and ascend our way up to positive terms. It's like, okay, I'm iterating through this tree. This could be a record, for example. And the like I would know it's a record because um because we keep these things. Like these aren't just getting deleted. These aren't getting deleted. Like nothing is going to none. We're not mapping any information to none. This is bad. Mapping stuff to none. We're keeping we're just keeping like a everything is separated into terms. It's like, okay, well, -1 means that we deleted it. +1 means that we kept it. And like nothing is lost. And then I think at that point we would only have to iterate through this thing one time. And then we just go through the negative terms first, delete the negative terms, and then we go through the positive terms. We add positive terms, and then oh my god. So I think before we were talking about compiling. Compiling is so much easier now because all it really means is combine like terms. So when we can compile expressions now just by literally taking the difference between the tree, combine like terms, which is pretty much a stateless thing. Like there actually is no need to post compile. You don't need to do that. I think you do it for every operation. So basically, in other words, we we literally just need semantics for this. We subtract the trees, and then we literally just traverse the tree, delete subtractions, subtract anytime there's a subtraction operation, we this is like something that we send over the network. Like this might be delete record, for example, right? This and then we perform the add operations, and we say add record, and then we just do that. Like that's it. That's literally it. We just do that the entire way through. Um, and obviously it's situational because in the case of going from off to on, we don't. This is stateless, so we don't actually have to. We don't have to do anything other than do like a patch request. We say, hey, on. We send this to the network. I don't know what. Yeah, the network. Here's our network. Here's a network. Here's Cloudflare, and then we say, okay, here's a record. Oh, except it's 0. So we don't have, it's 0, which means if it's 0, we don't have to do anything. Because 0 describes lack thereof change. So there's no change. So if there's no change, we don't have to do anything. If there is, okay, like we have to do change here. It's like, okay, well, we have to, what is this? Delete record. This is add rec. And we do it in that order. So this goes first, then this goes, and then 0. We don't have to do anything for 0. Minus record. What is this? Oh, that's just minus R2. It's like we just delete R2. Delete record. Do you see how fucking pretty this is, guys? Like, do you see it? Are you seeing it now? Do you see it? This is why semantics are so important. Right, so that's it. That's how you do it. So this is how we solve. This is how we solve the diff problem. I just deleted all that. Well, right, in other words, what we really need, unfortunately, is we need a class that does operator overloading stuff. Sorry, not a class that does operator overloading. We need a class because we need operator overloading, because the semantics are so much nicer. Like, look, guys, look. Are you ready? Let's write this function. So, oh my god, we don't even need push deltas. We just say def. I don't know. We're just gonna call it perform diff. We have an initial state. We have a target state, and the goal is to get the state to match the target state. So what do? We say, okay, well, ds, we get the d state is going to be s1 minus s. And then we have like, negative d state equals negative ds. And we literally just go through, like recurse nds. We literally just say this, recurse sub nds and recurse add ds. And then we have to figure out the implementation details of these. Oh, I'm sorry. No, this is completely contradictory to what I just described to you guys. We don't care about NDS because this encodes all the terms. So we don't actually need to subtract the tree. All the terms are encoded. So what we really do is recurse ds, and then we say, and then like basically recurse goes through the terms, finds negative terms, deletes negative terms, adds positive terms, and just replicates that. So yeah, we have to figure out the implementation details of what that means. But like I think the idea is there. So we can say, okay, we have a stack. We just have a stack, and like the initial state is ds, and we say, okay, well, stack is greater than 0. We iterate through, so we get the current equals stack.pop. This is our current thing that we're iterating. In this case, it's going to be ds. So our repeating case is our repeating procedure is that we are, oh, well, I fucking deleted everything. Like, it's literally as simple as we have this tree, and we're iterating through the elements, and we do that. So we could iterate this way if we wanted to. I don't actually know. What would be more meaningful? Is it better to iterate vertically? Or is it better to iterate horizontally? I don't know. I don't see, I'm not really good with algorithms, but I think probably we would iterate vertically, which means that the next element goes straight into the stack. So the first thing we do is put an element into the stack. Like if our repeating procedure is to, which in any case, our repeating procedure is to iterate horizontally, but the order in which we put that into the stack would indicate which level runs first. So I think we say, okay, put this into the stack. Put this into the stack. Horizontal. And then like there's nothing else we put into the stack because this doesn't have children. At which point we just run through the elements. Yeah, I don't know. I think that's how it works. So we have a stack. We pop the stack. We iterate through the elements. V in stack. I'm sorry, in current, and then we say, okay, stack dot push v. Yeah, no, this is actually going to iterate horizontally. This is going to iterate horizontally, I think. Which honestly doesn't. I don't know if it actually matters. I don't think it really matters. It doesn't matter. It doesn't matter. And then, so we pop a stack. We have ds. We're at ds. We're iterating through ds's children. So this is like a child. We push the child. And then so we're constantly popping the stack. And then, yeah, like what are we doing on each element? So this describes the procedure for each element. Well, other than pushing the children to the stack, the procedure that we perform on each element is to I think I just realized maybe this being vertical describes recursive, whereas this being horizontal describes a stack. I don't know. Maybe that's why stacks are better. I actually don't know if that's true. Yeah, I think that's how it works. So horizontal is faster than vertical. Maybe. Actually, let me search that real quick. Yeah. I don't actually know if that's what I don't know if that's what I wanted to describe. But anyways, also is push a thing or is it append? I think this is append. So, anyways, so this is I guess it's like a polynomial. It could be. This could be a polynomial. This just like it's just terms, right? So we have terms. So current dot like expression. Let's assume that each thing has an expression, and maybe each thing also has children. So each thing has children and an expression, and um, yeah, like we get the negative terms, and to be honest, I don't really know if, for example, if something is like -5, if something has like -5 as the coefficient, does that mean we have to delete it 5 times? Like maybe it does mean that, but I don't think we really need to worry about that. We're just gonna make it delete once. So let's just do this. We have an expression, and then we say like negative equals negative terms. And then we have positive, which gets the positive terms. And then we just say, okay, well, or I in negative, okay, term equals negative I. Or even better than this, is we get the expression. Even better than this, right, is we say, okay, expression is this. An expression is going to be a list of terms, which describes coefficient. It's going to be like ax. Okay, it's going to be like a times a, b, c. Right, and we only care about a. Right, so this describes an expression, right? We're not actually going to use c, but I think we better just implement it. I don't know. I don't think we need to. Maybe an expression is just going to be ab, right? So we say, okay, for, let's just say this. Yeah, a, b, and it doesn't matter. For I in expression, in fact, we could just inline this, so this becomes current expression. Well, term is going to be current. Yeah, you know what? We're actually going to do this. I'm sorry. We're actually going to do this. We're going to say expression is current expression I. And then we can say like term. We just say this. Okay, like if term dot a dot coefficient is -1, is less than equal to 1, right? Well, this is actually supposed to be greater than or equal to 1. So otherwise, term dot coefficient okay, we need to order. So the thing is, we need to order the ascending coefficient. Right, so we need to order it like ascending coefficients, otherwise this doesn't work. Because like we described before, we have to delete before we insert. We have to delete before we create. Right? We can't create and then delete. We have to delete first. So we yeah, like that doesn't affect this case. So we just say, okay, also the if it's less than -1, less than or equal to -1, right? So right, we do that. And then yeah, like that's it. So well, if it's greater than or equal to 1, then we add, we create something, like create something, delete something. And then like that's it, guys. Like that's really it. So we don't need this push deltas, we don't need all this stuff. We just perform a diff between we perform the diff between state 0. I'm sorry, state 0 and state 1. And state 0, honestly, I think we should just call this I don't think these need to be global also. These don't need to be global. This is going to be state. Yeah, no, that's it. Like that's it. That's literally it. We get the state. We create a new state. This is still up in the works. We perform whatever operations we do to create the new state, the desired state. Then we perform the diff between state and the desired state, and then this just works. But we have to make an expression class, and we also have to right. We have an idea of an expression, and we don't really need exponentiation, but an expression describes a polynomial, right? And then on top of that we have the cool list, and this isn't really a list actually. This is a cool list. This is like cool tree, or it might be a node. Cool node. It's a node. It's just a node. Also, I really have to poop, but yeah, like that's it. That's literally it, guys. So that's the idea I'm trying to describe, and yeah, hopefully our Cloudflare configuration will be back up, and I'm sick of this shit. Like, look at this shit, guys. Except this isn't really going away. Node is gonna inherit all this shit, but man, it's awful. You gotta admit, it's awful. It's awful that this is even a thing. Like, it's so fucking unclear to me what all this even does. So I don't care about it. It's not worth learning to me, and I gotta shit. BRB.